That's the minimum help you can do to yourself, I tell you. When I took my FE exam, it was horrible because I had to go through, I don't prepare well for the exams. So if you see me when I'm prepared for my exams, you would never believe that I would pass that exam. But, so that's why I would say, well, I'm saying the opposite way that I do. But, so please, use this book for this month before you go for the exam, as much as you can. Flip the pages, get familiar with these topics, equations, and page numbers, if you can. Of course, you won't be able to remember, but at least you have an idea where those things are. Like, for example, I'm going to point you out to certain important pages related to environmental engineering. All right? So, for example, if you go on to page 19 in this book, on the supplier reference book, you will see that it has some unit conversions over there. Do you see that?
Yes.
So that's how, like, I mean, you need to know just at least an order where the things are. That way you save your time. Saving time is most important in the test. All right. So today I'm going to cover you the topics on environmental engineering, as you all know that. So I'll be talking about few basics. What would be important for you to remember to be prepared for the test. So I'll go in this order. I'll go in water treatment, water quality, wastewater, and so on. So we will see the other topics like air quality, noise pollution, solid waste, and hazardous waste if we have more time. So, but I'll cover you more important topics that you need to know. All right. So your test would be on, as I said, I need help here. Can someone run to the department and get some more markers?
Where's it at?
I think that's awesome.
Okay, yeah, I can't hear, but I'm maybe running out of it. So we got water quality. All right, but thanks, Sarah. You're better prepared than me. All right. All right. Okay, so we're going to look at water quality and water and wastewater treatment. All right. So I'm going to give you some handouts actually. And we will look at some of the environmental regulations. Which is basically I would touch them on. Like I would like you to know what is CWA, Clean Water Act. But that's easy to say. But what is NEPTES?
Pollution Discharge Elimination System.
So NEPTES is National Pollution Discharge Elimination System. So you would find this kind of abbreviations being asked too. That could be as simple as that. All right. So basic units like I think I'm just running on the topics. Like Safe Drinking Water Act, right? So what does it do? It sets the maximum contamination levels, right? So this is about the regulations. We have Clean Water Act. It's the mother of all water acts. But under Clean Water Act, we have NEPTES. NEPTES is what is applied to all of the permits. If you are proposing to discharge certain waters, right, wastewaters into the receiving waters, then you need to have NEPTES. Then we have Clean Air Act. They all came in 1970s. Okay, we have Clean Air Act. So let me point out these 6 important pollutants. Please note down this. This is important for you. 6 important pollutants under Clean Air Act, or they're called criteria pollutants, or primary pollutants. Maybe let me say that, primary pollutants. Those are going to be your carbon monoxide, ozone, what are those? So there's 6 of those: carbon monoxide, ozone, it's called NOx. It could be anything. NOx means could be nitrates, nitrites, it could be even N2O and NO3, all right? NO. SOx, SO4, SO3. I'm not putting the charges here, but those. But 6 primary pollutants or criteria pollutants are this. So you may be tricked among these options. You may be put something else in there, and it can be. So let me tell you, like 10% of your questions will be something like you read and answer it straight away. You don't have to solve anything. So at least 10%. So that's the reason I like to give you some of these questions too. We can look at this. I think that's the easiest you can do in the test. Okay, then we have other acts. So when I say Clean Air Act, it's, you know that it refers to air. It is referring to air quality, air pollution control, and everything. Clean Water Act, it's for water. So now you have others like hazardous waste or solid waste. Okay, solid waste. They are covered under RCRA. What is that? Any idea? We talked about this in the class. Resource Conservation Recovery Act. All right. So that's there. Like I said, it's for solid and hazardous waste, and then you have different types of waste depending on. So you need to know what controls. So that is RCRA controls that. And there is CERCLA. Maybe I'll stop right there. That's CERCLA is another okay, this is difficult to remember, but comprehensive environmental response compensation and Liability Act. That's called CERCLA. Well, this is in short term called Superfund. Any idea what is this called? Why? What is it about?
So, is it like with who has responsibility, like from like until the grid? I forget what the term is for it. It's like who has responsibility for the hazardous waste.
Exactly. If that's a company, usually the Superfund is funded by the federal government to restore the conditions of those soils or those plants that have gone bankrupt, and they are given funding by the federal agencies to restore that. Actually, it's a Liability Act, but it's an act that helps those companies that have contributed to all of these hazardous waste, contamination of soils and everything. All right, could be water and everything. So you're right. But that's called Superfund, and these are like, you know, you want to know about these, just a kind of background. But if you read more about it, it would be nice. That would help you. This kind of simple questions you might get. So let's look at some units before I get started. All right. So milligrams per liter is what is concentration, right? Concentration expressed in milligrams per liter. And how else can I express? What's ppm? Parts per million. So if you get the answer either way, that's correct. So that's both same. All right. So this is applicable for your water. When it is water, your milligrams per liter is equal to ppm. All right. That's for strictly for water, not for A. Okay, so that's different. Air is different, different molecules and everything. Now, in environmental engineering, I can tell you for sure, if you don't get this mass balance concept, you cannot solve 90% of the problems. Mass balance is basis for everything, all right? So let's write. If I have flow Q1 and Q2, can I add, subtract, and do anything with them? So let's say I want to get a Q. Did you say yes? Okay. So if I said Q is equal to Q1 plus Q2, is that acceptable? Is that okay? Which means you can add, you can subtract, you can divide, you can do anything you want with flow. All right? Okay, add or subtract, we don't do anything else with that in our other applications. Then what? Your mass. Mass, let's say M1. So what are the units for flow? Units for flow. Cubic foot per second, that's right. So cubic meters per second, right? I think this is running out of use. I think gallons per minute, right? All of this. What's your mass? That's a point I'm going through all of this because you can make some fundamental mistakes that can give you wrong answers. Mass is kilograms, grams, anything, right? Pounds. Is that right? All right. So if I have mass 1 and mass 2, can I add them? Is that okay to add them? All right, that's good. So now we're talking about concentration. So I have C1 and C2. So I want to get a concentration. Can I do this? Concentration, I have two concentrations in two flows. Can we do that? No? Why is that so? You cannot do that. Simply you cannot do that unless your flows are same, but your concentration is not additive. Okay, I just need to tell you that. That much is enough. Even if you are concentrations are not additive. All right. If you are calculating, suppose concentrations now, how do we get? Milligrams per liter we said, grams per liter, pounds per gallon. All right. So all of these. Now, if I want to get mass, I have flow and concentration. Flow and concentration. So which means I have Q and C. Can I calculate mass? What's the formula? What's the formula? Q? What's mass? Q times C, right? Is that clear? So which means you have two flows. And then if you're looking at that, let's assume that you have two environmental flows, all right? There's a river going in, and then you have a flow coming in and joining the river. So the river originally has a flow of Q1 and a concentration of C1, and then you have a waste, all right? This is waste, and this is river, and concentration of C2, all right? So at this junction, you want to know the resultant concentration. How do you get that? So what's the Q at this point? How can I get Q at that point? So it is okay to add Q1 and Q2, right? Q1 plus Q2, because Q1 and Qs are additive. And then I cannot do for concentration. It's not true for concentration. So then what I do?
QC equals Q1.
Exactly. So which means which is called mass balance. All right. So we apply the concept of mass balance. Then we say QC is equal to Q1 C1 plus Q2 C2. So now what you don't know is you know Q. So C you can get by doing this, right? So this much background is sufficient to just move on. Let's go on with the very first example I have on this page. So when you get this handout, the single page, look at problem 14 and tell me, can you solve that problem? The single handout, this one, it will come to you. Actually, I think I have more than 30 people. Yeah. 14? 14? Yes. You can? All right. 14. 3 wastewater flows, right? 3 wastewater flows. So what I will do is, we'll read the problem quickly. We'll think of the strategy, how to do the problem. We will see if we have time, we'll do the solution, but at least you write down the procedure. I'll give you the answer, what it's supposed to be, and then you go on. I'll do some problems, but we have 2 hours to do, so we'll see how many we can do. All right? So 14, if you see, we just discussed about that. All right? So 3 wastewater flows combine in a sewer. So this problem has, everybody got these sheets, right? 14. So 3 wastewater flows combine in a sewer, each having flows and BOD concentrations as follows. All right? So you are given the flow and the concentration. Is that right? So Q1, Q2, Q3, C1, C2, C3. Now, if infiltration is 10%, having 0 BOD, all right? If infiltration is of the total flow, okay, here is the trick. If infiltration, I'm also reading for the first time here. The resulting BOD is most nearly. All right, so how do you solve this problem? What is your Q here? So you need to know, you know Q1, Q2, Q3. Given, right? Q1, Q2, Q3 is given, which is nothing but all of this when you put, that's going to be Q. That's going to be Q. Is that right? Now, the Q, and now you see that you have Q is equal to, I mean, QC is equal to, that's the question is asking you to do. C3, but there is 10% infiltration. Did it say that? 10% infiltration, which means you lost, there is BOD concentration in all of these flows, so C1 is nothing but your BOD. By the way, what is BOD? Biochemical oxygen demand, right? That's right. So there is infiltration having 0 BOD, so which means you lost some water, some wastewater, but you didn't lose BOD. That's what it means to stay. So which means you have 0.9 times of Q. All right? And C. And then you have all of this term. So can you calculate C? What you don't know is C. Is that right? Is that simple enough? That's the problem there. You want to crunch numbers and tell me what the answer is? Take a minute and see whether you can do that. So actually this problem has a different solution, but I'm going to take this as, so this is wastewater combined with sewer, and infiltration, okay, infiltration is not into the ground, but actually, so that's a fourth floor, so it's more now complicated. It says like there's a fourth floor, but I think you do the way I asked you to do, so maybe that could be easy to do. So what you can do is you can ignore the 10 power 6. That's common in everything. So ignore 10 to the power 6 and just take all of the, take like 4, 0.8 and 0.2. That's how you simplify the problem. You don't have to use a big number, right? Because 10 to the power 6 is common. So exclude that from all of your numbers and then use that. All right, so take this. Okay, let's just modify a little bit this question. This problem. So what you do is there is a Q4 with a concentration of 0. That's what it means. So it took infiltration to be entering the flow, which means there is what's that? 10%. It said, yeah, 10% of the total flow. It said, which means your Q4 is equal to 0.1 times your Q. All right, so please include this here, Q4, C4, and now you know QC, and then that's you. So you see, how much is your C? Did you follow the concept? So here infiltration, it is taken as the flow actually going into the stream actually. So which means you have 4 flows. The fourth one is actually is 10% of the total flow. So all the 3 flows. Then you have the mass balance, QC, your total concentration is equal to your 4 flows, and then the constant, that's how you get it. So the answer is 207 milligrams per liter. So turn to the page on the other side. Please read problem 15. Well, actually, it's a long problem, so I'm just debating whether we're going to do that or not. It's a long problem to read, so it's going to take a minute for us to read. So read 15. So you're given that's for 2 problems. So a municipal activated sludge wastewater treatment plant with primary clarification and anaerobic digestion has the following influent characteristics. All right, so you're given flow 5 million gallons per day. So MGD is million gallons per day, right? BOD 5 is 200 milligrams per liter. So by the way, so your wastewater treatment plant, so if you see the wastewater treatment plant, there is a primary clarifier, okay? As the wastewater enters the plant, so a plant will have a primary clarifier. If you remember from your wastewater class, it would have a biological treatment unit, okay? Biological treatment unit, which could be activated sludge process or trickling filter. Are you able to see this? Such a bad day. Don't get activated sludge process or trickling filter. All right, so that's called a biological process, biological treatment process. Then you have secondary treatment, secondary clarifier basically, and then the discharge, which is called effluent. All right, so primary clarifier basically removes solids, okay, suspended solids, like up to 60% of the suspended solids are removed, solids. There's no treatment. This is only physical separation. Just so you know that in primary clarifier, there is only a physical separation of solids. There's no treatment involved there. And there is BOD, biochemical oxygen demand. Depending on the design, okay, you can also remove up to 40% in this unit. All right, so the remove, and after that, if you see, it would be tricky how much it would be removed here to say. It's something like anywhere between, the BOD will be removed anywhere between 40 to 55%. So finally you have anywhere the removal between like 90 to 100%. It's hard to, I mean, it is possible, but 100% of the BOD removed, okay? So the problem is saying, you know, you have a flow here, flow is coming from here, and that's 5 million gallons per day. So, by the way, how many liters is 1 gallon? How many liters is 1 gallon?
4.
4. So, but you can't use that number 4 in the exam. You got to be very accurate, right? Otherwise your calculations will be wrong. So, who knows the answer?
3.9.
You're getting close. And
3.785.
okay, you got it from the book. So 3.785 liters, right? So million gallons means 10 to the power 6 liters, 6 gallons. And then, so there is a lot of conversion involved here, unit conversion here. Then this problem I want to say is, what I want to say, you will be surprised to see what is being asked in this problem. So you are given the waste sludge flow rate. That's going to be from your clarifier. Some of the waste is going to, so that's what it said. So 0.1 million gallons per day is being wasted. And then the concentration here, mixed liquid suspended solids, concentration here is 25 milligrams per liter, 2500. Then there is a return activator sludge concentration that's going 6,000 milligrams per liter. Okay, that's return sludge. Then aeration basin. Aeration basin detention time is 10 hours. Okay. Primary clarifier overflow rate 900 gallons per day or square foot. And then effluent BOD, you're given effluent BOD. So you're starting with 200 milligrams per liter BOD. And the effluent BOD is 10 milligrams per liter. Or final is 10 milligrams per liter. Okay, so if the plant BOD5 removal efficiency is 95% and the primary clarifier removes 35% of the influent BOD, the amount of BOD removed in the biological reaction is most nearly. So the question is, if the total plant, the whole plant has an efficiency of how much? 95% removal of BOD, right? That's what it said. And your primary clarifier, so this part of the system removes 35%. So are you going to say that this has removed 65%, but how are you sure if it is not that way? Removed in the biological process nearly, well, okay, that's what it looks like. But the amount of BOD removed, pounds per day, so your answer is pounds per day. Whenever you're looking at the answer, before you solve the problem, it's good to know what is being asked. So that way you work your solution towards those units without wasting your time on working on other units. So what would be the strategy on this problem? First of all, tell me what you need to know. It said how many pounds, what's the amount of BOD5 removed in the biological reaction? First of all, what do you need to know? What's the strategy to solve this problem? It is a big, it looks like you're given a lot of tons of information. You won't use all of it. You only use a little bit of it. It's given to divert you, all of that. Okay, so you won't use all of that information, but it's the question. The question being asked is very simple, and the answer should be also supposed to be simple. But if you practice enough, it should be simple. So, what's the strategy? What do we need to know?
We need to overflow rate? We need to use that one?
You're already okay. Wait, you're already given like 95% and 35% removal efficiency. So again, you don't use that information. See, I said you're given that information. This I gave you for an example, for an idea. Okay, probably I should remove this. This is not part of the problem. These, okay. I basically try to give you some background and then what's the problem. That's how I did last time. So now this problem statement says this is the total amount of BOD entering the plant. The whole plant has 95% removal efficiency. And if your primary clarifier can remove 35%, so this part can remove 35%. And how much was removed here? It is not asking you percentage, but it's asking you how many pounds per day was removed. All right? So this unit, how much it was removed, it was asking. So how do you do that problem?
Could you add up your total? Would this be a mass balance for the sludge?
It is a mass balance for the sludge. You're right. So you need to know how much is entering the plant, right? How much leaving the plant. Then you know. From then you know that how much was removed in the system, which means like 95% was removed. Is that right? So let me write first by step. First step is okay. Are you following me? So first what I'm going to do is, I'm going to calculate the total BOD in mass, pounds per day, and then remove the 35% removed from there. And then if you notice, about 5% is leaving. In the problem statement it said, 95% means 5% is leaving, right? So 5% is leaving over there. So let's do it like this. Let me put the numbers together for you so you understand that what I'm trying to do. So influent BOD. It's 200 milligrams per liter times the total. So I'm going to put it in pounds per day. So that's 5 million gallons per day, and then therefore 8.34 pounds per million gallons per milligrams per liter. So this you need to know, this is called a magic number, 8.34. If you want to convert milligrams per liter into pounds per million gallons, okay? Okay, that's only a conversion. You can take it like a conversion factor, 8.34. So I know now the starting point. That gives me how many pounds I have. Then the first step. And the second step, 35% of it was removed, right? Primary clarifier removes 35%. Therefore, you have 2919 that was removed. Now, how much is leaving? 5% is leaving, right? So you know, even you're not using this, but you could use that. But you don't have to use that once you have that number. So effluent that would be 417 pounds per day. So now you see, so what is entering is here, and there is one outlet here, and there is one outlet here. What is removed here is this minus this and that. Is that right? So your BOD removed in biological treatment would be 8340 minus 2919 minus 417. That would be your answer. Let me see how many of you do the second one. Okay. Is that clear? So you have 100% coming in, 35% removed by the first unit, primary clarifier, and then 5% is leaving the system. So the remaining 60% is supposed to be removed by this unit. Actually, the shortcut for this problem would be to multiply this with 60% would be your answer. Is that right? That could have been a simple solution, I think. Yes?
What would tip you off, like to know to do that? How would you see that shortcut?
Shortcut? See, I went through the long route, but I just recall that it's as simple as that. So you have 100% coming in here, 100% coming here, and 35% out of 100%, 35 is removed here, and 5 was removed there. So how much is removed here?
That's all it is.
That's all it is. So first step, well, you really, either way you need to do the first step, and then if you multiply this with 0.6, that would have been your answer. Is that right? Please read 16. That's a very straightforward problem. 16 is connected to the 15. They're together. Same problem. Just let me know how you want to do this problem. So the aeration basin volume is most nearly. What information we need? We need to calculate volume. The simplest way of calculating a volume would be what? Flow times time. That's right, Brent. Volume is equal to Q times T. Right? So do you have Q and do you have T in this problem? Statement. So only thing you have to convert them, I think, because but okay, your answer is in gallons, so you may not need to do that too. Only from days to, so this is 5 million gallons per day, and then you have here 10 hours. So let me see. That right? Let me know what answer you get. About 2 million, right? So the answer is C. T is nothing but your detention time. Sometimes it can be called detention time. All right. Now this is really a complex topic. You have different terms called solids retention time. T is nothing but T is detention time or hydraulic retention time. Okay, hydraulic residence time, I would write it like that. Hydraulic residence time, which is nothing but HRT, detention time, HRT, T or theta, they all mean same. All right? The reason I'm writing this is there is another term called theta C. All right, theta C is solids retention time. SRT, in other words. Solids retention time, or this is also called as cell mean residence time. So that is CMRT. That means that the first one is related to your wastewater. This one related to wastewater. This one related to your solids. All right, biosolids or cells. As it says cells, which means the residence time of the microorganisms. So I'm going to write this as biosolids. Okay, pay attention to those terms. So there is mean cell residence time. Actually, cell mean, I said mean cell residence time, so MCRT, and a solids retention time, so SRT, and a hydraulic retention time, and all they are all different. So pay attention to those. Right? So what does it mean? When some of you can recall, what is the solids retention time or mean cell residence time? Mean cell residence time. What is that? But it's the time, theta C is the time by how much time the microorganisms live in the system. They are here, they enter here, or actually, or they are in this loop, okay? In that loop, how many days they stay. This is wasted, so biosolids wasted every day, okay? Waste biosolids, and this one is recycled. So which means the biosolids are being recycled, and then they are in this cycle for so many days. Your theta, so the difference between, so you need to know, when you see theta, theta would be somewhere between 4 to 8 hours. All right? But your theta C is anywhere 5 to 15 days. Why is it so? Theta is water flow rate, okay? Just water is entering through and then goes out. But your biomass, your microorganisms, they're staying in this loop for so many days. That's why it's 5 to 15 days. That makes sense to you? And if you notice here, there would be some correlation between these two, because I'm wasting like 10% of every day. So which means they are being here for so many days. So that kind of ratio over there. All right. Those are the differences. If you go on to the other, the problem 13, you all should be able to do. Do you have a question on that? It's like more of a chemistry type of problem. You are designing an aerobic system to biodegrade benzene. The biodegradation follows the chemical reaction below. You've given the molecular weights, and the benzene concentration is 500 milligrams per liter. The amount of oxygen that will be consumed to completely biodegrade the benzene is most nearly. It's nothing but the concept of theoretical oxygen demand calculations. Do you remember that? Theoretical oxygen demand. Theoretical oxygen, so you need to know the chemical reaction. Actually, you're given the chemical reaction here. So which means 1 mole of benzene, okay. So you have a task here, right? I see that. But is that equation balanced? Please balance that equation. go straight to the problem. C6H6, all right, plus O2 gives rise to CO2. See, always when you have carbon, an organic compound, reacting with oxygen, your product is always carbon dioxide, all right? And because it has hydrogen, and because there is oxygen involved in the reaction, your second reaction product definitely has to be water. And because this reaction is aerobic, again. So now you got 6 carbon here, there's supposed to be 6 carbons here. So did I balance that? Is that right? Now I have 6 hydrogens, but I don't have 6 hydrogen here, so I'm going to balance hydrogen 2. Now what is not balanced? Oxygen. So how much oxygen should I have? 6 times 2, 12. 3 times 1, 3. Supposed to be, because I have 2 here. Is that right? Okay. So how do you do this problem? The amount of oxygen, milligrams per liter, that will be consumed to completely biodegrade. So now you know that there is at least a relation 1:7.5, right? For every, that's clear, right? How I got 7.5. So your benzene, for each of the benzene molecule, you need 7.5 moles of oxygen, all right? So that's clear. So again, this is molar relation. Okay, the relation is based on moles. In your problem statement, you are given 500 milligrams per liter, which means, can you use it straight away? It's not 1 kilogram and 1 kilogram, or 1 pound or 1 pound. It's moles. So which means we need to convert 500 milligrams per liter to moles, right? So you are given, you're not given the molecular weight, so you have to calculate the molecular weight. Can you do that? For benzene, molecular weight would be 12 times 6 plus 6 times 1, that would be 78. Right? So you're given milligrams, therefore the units would be milligrams per millimole. Is that right? Yes?
Wouldn't it be better to convert moles 7.5 to milligrams per liter since our final answer is in milligrams per liter? So we're going to have to convert back to.
So, one more, which means 7.5.
Wouldn't it be easier to convert from 7.5 to milligrams per liter since your final answer is going to have to be in milligrams?
7.5. You can do that, but you still need to know how many moles you have because that's a ratio, right? 1:7.5. You can do that way too. That's nothing wrong. What I'm trying to do is, if 1 mole requires, 1 mole of benzene requires 7.5 moles of oxygen. You guys are smiling. That's good anyway. Keep smiling. So 1 mole requires 7.5 moles of oxygen. So, which means, now how many moles I got in benzene, right? So if I know, then I can straight away say those many moles. But again, for oxygen, your molecular weight is different, so then you get that into. Yeah, it's like at least 2 steps process, this one. And I'm going to write the problem, the solution straight away to solve some, to save some time. Then I'm going to put milligrams of O2 per millimoles of O2 per millimole of benzene. So you have so many moles. 1 mole of benzene requires 7.5 moles of oxygen. Therefore, if so many moles of benzene you have, this is benzene. So units, this and this will be cancelled. All right. So your millimoles per oxygen will be cancelled. And this is molecular weight. and therefore you will be left with, finally you will be left with milligrams per liter. Okay, the answer is supposed to be 1540. The answer is D. Okay, let's move on. Take the other handout you have. Can I borrow a copy? Do we have extra copies here? So let's turn to page 2 on this handout. I'm going to talk a little bit of discussion here, then we go on with problems again. So I'll be making you to flip pages. Second page on this handout. Which of the following statements, I'm reading the bottom question. Which of the following statements are true of facultative bacteria? April.
Yes.
Facultative bacteria require oxygen as electron acceptor for metabolism. Okay, by the way, facultative bacteria, do you know what that is?
Nope, I just
They need oxygen. Let me read before I give you the answer, let me read all of the options here. Facultative bacteria cannot use oxygen as an electron acceptor for metabolism. Facultative bacteria require nitrate all right. So the answer here is tricky. It's not that straightforward. Okay, so that's the reason I'm asking you. Do you know what is facultative bacteria? No. It's not related to faculty, all right, first of all. So it doesn't relate to me. It's not my relative. Okay, facultative bacteria is the bacteria that works in wastewater treatment plant. So the bacteria that are responsible for wastewater degradation or cleaning or treatment are called facultative bacteria. Why they are named that way means they can live both in aerobic and anaerobic conditions. All right? Aerobic or anaerobic, or I should say not anaerobic, but anoxic conditions. They require oxygen, but that's not entirely true of them. They can also live in conditions where they have limited oxygen or some other form of oxygen. Anoxic. Anoxic means, so aerobic, if you remember our water class, aerobic is oxygen, has to be oxygen. Anoxic, pay attention, anoxic can be your NO2, sulfate, anything like that. All right? So anaerobic. Anaerobic, strictly no oxygen. No oxygen, but can be carbon dioxide. Right? And methane and those things. So, do you think any of those three options are completely true of facultative bacteria?
No.
Sarah, what's your conclusion? I said facultative bacteria can live in both aerobic and anoxic conditions. They don't have to be having oxygen all the time. They can also thrive in other conditions like nitrites and nitrates, sulfates, and others. But if they have, as long as they have some form of oxygen. All right? So which means the answer is none of the above. Let's look at another one too here. Okay.
Any kind of way we could have done the process of elimination without knowing what that means?
Okay, that's good. You asked me right question. Facultative bacteria require oxygen as electron acceptor for metabolism. That's correct, but that's the reason, before I gave you the answer, I wanted to read entirely because it cannot be that simple too. Your question cannot be that, it can be tricky. That's the reason I wanted to read entirely before. And second one, Cannot use oxygen as an electron acceptor for mechanism. Cannot use oxygen. That's not true too. They can use oxygen. So, which means first one is not entirely true, second one is not true. Okay? Third one, facultative bacteria require nitrate as an electron acceptor for metabolism, which means they're saying they require, which means it's like a must. But it's not a must. They can also use oxygen. Right? That's the point there. So turn to page 4 on this. I'm going to make you do different variety of problems. That way you get hands on everything. Fourth page, like a lot of discussion questions. If the bottom of a lake is anaerobic, okay, pay attention. The very first problem, right? If the bottom of the lake is anaerobic, what form of nitrogen would you find at the bottom of the lake?
C.
That's right. So I think I taught you enough. What are two ions responsible for nutrient enrichment? Nitrate and phosphate, calcium and phosphate, think carefully, aluminum and nitrate, nitrate and sodium. Sure?
B.
B?
A.
How many A? How many other than A? A. A is the right answer. Nitrogen and phosphorus, in other words. Effects associated with excess nutrient enrichment, and sometimes these options you find can be funny too. I smiled sometimes when I saw the options. So, effects associated with excess nutrient enrichment in surface water is called global warming, biodegradation, eutrophication, and fermentation. Which one? C. How many of you C? Is it not global warming?
That's what I said.
All right. So C. C is the right answer. A lake which is, I remember this question, I got it from in my test. A lake which is low in availability of nutrients is called eutrophic. You think it's right?
No.
Eutrophic means excess, right? Mesotrophic. By the way, what is mesotrophic? You know benthic. So eutrophic, you can take it off. And D is benthic. Do you think benthic is an answer? Benthic related to what? Where? Benthic means? Benthic. It's sediment. Right? So which means it's not. And then mesotrophic. Did you hear about mesotrophic? You should not have heard about it because I created this. There's no word mesotrophic. Matthew will say yes. All right. This, I put it just for fun. All right. So the answer is C. So the log inactivation of Giardia, to meet the requirements of the surface water treatment rule is most nearly. The surface water treatment rule is not the regulation that establishes Giardia inactivation requirements, or 2.0, a natural log of them 10, and then 3.0. What is that? I would say safely it's 3. So 99. Oh, by the way, what is log inactivation? Or log removal? I make this joke a little bit sometimes. So what's this? Log inactivation. Or log removal. Oh, somebody says, oh, we have 3 for log removals. What does it mean? Is that?
99%.
Is that by 1 or 10?
Yes. Like 3 log removal means 99.9%. All right. 4 log removal means 99.99%. It's not that they're trying to remove logs out of water. So it's in industry. The term is log removal. So you say, hey, how many logs you got? We got 4. So they tell you they're over there. So it's there. It doesn't mean that So they're removing logs, but it's log removal. Okay, log inactivation.
All three is
Okay,
how
all
much?
right. I teach you log inactivation. Okay,
All three is how much?
99.9%.
And you said 4 log was what, 100?
Like it goes down. Yeah,
That's like the sigma rule, like 3 sigma is.
yeah, something like that. Whatever makes sense to you. So, all right. So is that enough, or we want to go ahead?
It's like 1/7.
So these,
Is it D? Is that the answer?
which one? Oh, D. Yes. Okay, look at this one. The concentration of chlorine on the same page, the concentration of chlorine at the break point indicates the presence of the concentration of chlorine at the break point. By the way, where is that break point coming from? So if you remember anything about the disinfection, you will see that this kind of curve like that. All right, this is called a break point. All right, this is called break point. This is chlorine addition. Actually, chlorine addition here, and your chlorine, and then chlorine compounds. You know what happens when we add chlorine to the water to disinfect? We disinfect water with chlorine, right? Chlorination. So when that kills bacteria, so some of the chlorine is utilized to, it's taken up by ammonia, all right? And they form different compounds. At a certain point, and you keep adding, so that's why this arrow is going, when you keep adding chlorine, it will happen that at some point, all of the chlorine is freed off all of these reactions, and then it starts to go up. That's called the answer. I think I gave you the answer. That's free chlorine. All right? One last this thing we'll see, and then we'll do some problems. Also, I think that's another interesting. So the presence of heavy metals. The next question: the presence of heavy metals in dewatered wastewater sludge would cause the following concern: poor dewatering characteristics leading to wet sludge. A. B. Chemical reactions between the heavy metals and the soil. C. Binding excess water in the soil during winter months. And D. Elimination of land application as a viable disposal alternative. So which one would be this?
B.
Which one?
B.
B, you said? Okay. Tell me the right answer.
Clearly. A.
E.
Who said D? Basically, of course, all of those reactions take place, but the primary concern is if you have metals, the rule is that you cannot apply on the land. You cannot use that water or sludge. You can apply. So that should be the simple answer for that. Sometimes you get these options, but you will see, because you're not sure, poor dewatering characteristics leading to wet sludge. I don't know. I'm an environmental engineer. I don't know about that. B, chemical reactions between heavy metals in the soil. Not sure, but it may happen. So you see the probability over there. But what you need to know is actually if there is metals, that's the rule. Heavy metals, which means they're concern, health concern. So they definitely are not allowed for land application. So that you're sure. That answer is, it's a confident answer. One more on the last page, at the bottom. Which wastewater quality indicator has the highest percent removal based on typical influent concentrations and effluent regulatory criteria? Which one is that? So which means, in other words, what's the question asking you?
D.
Who said D?
D.
Which one?
D.
D, no.
C. C. It's C.
C. C, no. Who said B? B, 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 B. 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 That's right, B. I'm trying to convince you all, but you don't convince. That's fecal coliform. It's, you know, if the units, if you see the fecal coliform, the units, like they start with 10 to the power 6 per 100 milliliters. The unit. Your BOD is just how much? 200 milligrams per liter. It's low. Your fecal coliform is so high. But then, once you treat the wastewater or water, everything, at the end, they almost go to zero. So, which is the highest reduction? Which means it's asking you which pollutant or which concerned compound or pollutant in that water quality has been reduced maximum. Like if you look at it, then it has been removed like 5 log removals, right? In our language, 4 log removals at least, right? So that's the highest. pH, it may change by a few units, but when you look at the percentage, it's not big. And BOD, it's 90%, or 95%. But when you look at this amount, you're starting with and then ending with, that's what the question is about. Did you follow the logic there? All right. So let's go back to the front of the thing and then look at the. Yeah, let's do different problems here. The very first one, if you do that, then you will know. Very first one, a rapid mixing process. By the way, where is this rapid mixing process coming from? Where do you see this? Coagulation, right? That's right. Coagulation. But where do you see this? What for? Water treatment, right? Water treatment. So now I just show you this wastewater treatment plant. Now this is going to be water treatment plant. All right. Water treatment plant. You have rapid mixing process (RM), and then you have a flocculation basin, and then you have a sedimentation basin. So if you remember this train, I think I drew it like a couple times in your class. This is a flocculation. When you have filters, finally, these are filters. So, that's right, rapid mix basin is also called coagulation process, right? This is flocculation. Now, just to brief you on, this one here anywhere between 0.05 to 1 minute, the residence time or the hydraulic detention time for rapid mix would be anywhere between 0.05 to 1 minute. Okay? For your flocculation, that would be anywhere between 15 to 45 minutes. All right? And this one would be between, I think now is like 2 to 4 hours, I would say. The detention time increases as the water flows through. Water is flowing through, okay? So water is flowing through, and you are removing the sludge right there. So the sludge is nothing but your solid particles, the suspended particles, bacteria, you can call it anything you want. All right. So if you see that with detention time, your tank size is increasing. Is that right? That's all you need to know. Okay. Now read this problem. A rapid mixing process. But by the way, you have to recall what happens in this tank, right? The first one is to just add chemical. just to introduce chemical and mix it well. That's it. And second one is to do a slow mixing. So this is very fast mixing. That's why it's called rapid. So rapid mixing, and this is slow mixing. It's done slow mixing to make sure that the particles come in contact and they become bigger in size, because they have sticky surfaces, so they become big. And by the time they go through compartment 1, 2, 3, and then come out here, they are like big, right? So they settle down. But water will flow. Water will flow out, but your particles will settle down. That's the idea of sedimentation tank. So you're starting with particles here. Your raw water has particles. You cannot even see that. Actually, you should ask Sarah. Sarah is a specialist now in this process. She worked with me in the summer. The particles, you can see the color, but you cannot clearly see an individual particle that much. So that's difficult also to remove here. But when it goes through here, you are introducing chemical, and then you are mixing with the water, mixing the water slowly such that the particles grow. And then the particles that are growing there settle down, and then you do the filtration. And then, of course, finally, what do we do here after filtration? Anybody? Chlorination. Could you use the right word? What's that? Use the wrong word. Chlorination, I said, but can you use the technical term for it?
Disinfection.
Disinfection, I'm happy. So, disinfection. All right? So that's what it is called, chlorination, in other words. It's so much used, so much so, you just get it, chlorination, but not the answer. Okay, read this problem, first problem, please. A rapid mixing process must provide a minimum hydraulic resistance time of 45 seconds. So is that within this range, 45 seconds? So you're given the detention time of 45 seconds. So just grab it as soon as you see this. And then Q is 0.3 million gallons per day. Two identical tanks. It says you got to design two identical tanks, which means, what does it mean? Your flow is split into two. All right, just hold on. And if the tanks are cylindrical, you are given tanks are cylindrical. Number two, two tanks, and then they are in cylindrical, and with a liquid depth equal to radius. All right, so radius we don't use radius anymore, so I'm surprised this problem. The minimum depth is most nearly cylinder. So what do you need to know first? So it's asking you to get the depth. So the radius is equal to depth, and then it's asking you what's the depth. First of all, what's the volume of cylinder? Pi r squared L, right? L is length, right? So, but here length is nothing but your depth of the tank. All right? So I'm going to write it as pi r cubed, because L is nothing but your D is nothing but R. That simplifies your problem. So now all you need to know is V. How much is your V? Once you calculate V, 0.3 times 45 seconds. Well, you see here you got me. What's the answer in? One answer is in feet. Okay, now you need to know 1 cubic foot is equal to 7.5 gallons. You need to know that. Okay. divided by 86,400 seconds times. Am I missing anything here? I think I converted this to days, but okay. This is in million gallons per day. That's why I put it as 10 to the power 6 gallons. That's per day. So for that reason, actually, I'm going to, per day you have 6,400 seconds. So everything will get cancelled. You get your answer in gallons. Is that right? Once you have the volume, how much is your volume? So I have the direct answer over there. So if you know the,
Wouldn't you have to divide it by 2 since it's 2 identical tanks?
yes, I did mention that you can do it now or you can do it later. So you're right. So let's go ahead and do it, right? 2, because 2 tanks. How much is your, okay, go ahead and do it. What's your volume? Once you know the volume, convert that volume to cubic foot and then get your radius. Then you know that, right? Harrington, how are you doing?
I answered it.
You good?
Yeah.
So you got this, Raju?
Yes, sir.
You're some Davis, I don't remember your name. Are you last name Davis? Let me guess your name, I forgot your name. You were there in my class, right? I'll forget. I'm waiting for you to give me the answers.
What is it?
1.82 feet.
See, Ben wants shortcuts.
Yeah.
He wants answers straight away. So what do you think is the answer, Ben? I'm going to ask you back.
It may not be right, but that's it.
What's your guess?
1.5.
What's that?
1.5.
Oh, you're very close.
So is it very right?
That's right.
Obviously so.
So how many of you got 1.5? You didn't do this. You did? So you should get 1.5. And so then you equate that with let's move on. Now this is a different problem here. Can you read the problem on the next column? Oxidation of iron in a groundwater supply is described by first order kinetics with a rate constant of 5 per hour. Oxidation first order kinetics, by the way, what are those? What's the formula for that? Suppose if a contaminant is being degraded or increasing, or decreasing or increasing, following a first order reaction, how does it look like? I mean, what's the formula? Do you recognize that? So CT, I mean, your concentration at any time is the so that this is the first order kinetics, which means you're going to use this formula. So immediately you want to look for that formula, okay? So by the way, in this book I was supposed to tell you. So starting with page 170, you will have environmental engineering section. So, like most of the class is over, I'm telling you now. So, page 170 is, let's see where we have this reaction. That's going to be on page 176. Yeah, that's 176. You see the first order over there, right? So the last table, it shows C is equal to your concentration is equal to at any time. That's what you see. So please read the problem. So you're given rate constant, is that right? Rate constant. And untreated ion concentration. So untreated means your initial concentration. Is that right? Initial concentration is 1.8 milligrams per liter. And 90% is desired. So 90%, which means you are given the final concentration. Is that right? 90% is desired. So your final concentration would be 0.1 times 1.8. Is that clear? So what are we calculating here? T. So the necessary hydraulic residence time, we don't even read the problem, we know that what it is asking for. Yeah, these are very straightforward problems. So T, they're calling it as hydraulic residence time. So that's what it is. Tell me what is your answer. 6. So what's the time? 0.8, somebody said? Which one?
0.406.
No, sir. Hey, you are making a guess or are you doing the problem?
0.02?
No, I did it.
Did you did
I
it?
got it right here.
Okay, where did you get this? Okay, you got this. I think this was wrong. I got 1.8. How many of you got 1.8? 1.8. How much? 0.46. Yeah, you have to. Then you can take the.
When you divide by 1.8,
Yeah, you divide by 1.8, right?
yeah.
I can negative 4.6.
Okay, let's do this way. That's where I'm coming from. So your K, you're given 0.5 and T. Can we do that?
That's right.
So you are looking at like, you can just take it the other side. Actually, you're right, divide, sorry, yeah. I see the mistake already. Yeah, you have to divide by that. So, but if you write it in log way, log form, then you can do that. But still got 0.46?
I got 4.6. I got 4.6.
Is it?
0.4605.
E is the.
Oh, I forgot to put negative.
Because it's a full rotation. And it says.
Now it's 0.4605.
Hey, Gude, I might have an answer or solution to your problem.
Yes, go ahead.
Where it says the problem is like a reactor.
This is a reactor, that's what I'm looking at. So I'm trying to give you the correct formula.
C equals sigma over 1 plus K. Instead.
But that doesn't have. What'd you say?
That's still
What does it say?
That's true, isn't it?
Wait, what is that?
Where are you going for? What are you using for workload?
See it?
Yeah. Or battery. You just say C.
Oh, yeah.
I'm good.
Yeah, roll that phone, yeah.
Really?
Yeah.
No. This is completely understandable.
I think for some part, you can solve it.
But if we do it that way, then we'll come up with a negative answer.
But is this one ideal?
Yes, you will. I think.
It says completely.
Okay, so which formula should we be using here? Which one? Which formula we need to, in the table, if you notice the table, so this is first order reaction and everything is right. So the formula is C over C naught minus 1 over K.
But that gives you negative though.
No, that's not going to give a negative.
C naught over C minus
So let's do this.
What's that equal to?
So when I put it 1.8 minus 0.18 over 0.18 times 0.5. So that should give you 1.5. That's from your equation for theta for that reactor. So it's following first order reaction, but it's in a completely mixed tank reactor. So were you mentioning about that equation before?
Yeah.
Yes, that's right. So that's going to be your. I did not notice the CMFR. You say a complete mixed tank reactor, right? So I did not notice that statement that said complete mixed reactor. So that's where I think we started to work with. But the principle is same. Your principle is first order, but everything is correct. So this is going to be your 1.5 hours. So 1.8, right?
No. No.
How much you get?
It's still coming out negative.
It's not. It won't be negative. That I'm sure.
But look, okay, but this up here,
It won't be negative.
I need it.
I'm going on more.
Oh, I have a question.
All right, I'm
No.
It counts off 5.
This is not negative.
Dr. Gude,
Yes.
can I ask your help there? But I guess I can do it simple math. Okay, this is the one we started with. C equals over 1 plus K theta, right?
Yeah, I think when you rearrange this, you will get the same thing.
That's not sure. Well, we do it like that. Okay, so it's C equals C naught over 1 plus K theta. To simplify that, it's C times 1 plus K theta equals C naught. And you do 1 plus K theta. But that's the formula. 1 plus K theta is 1.
Oh, yeah, yeah, you're right.
That's the formula for first order.
This is the formula because you do the concentration. You should make it your capital in theta. So you need to okay, just want to clarify with you. Here the problem statement. The mistake that happened with me is that I did not notice the complete mixed reactor. Okay, so I did not notice the complete mixed reactor part of it. So then I thought I assumed the first order reaction and went up. If you notice that. But now this solution is, if you're wondering where I got this thing from, you have two tables over there for zero order reactions, first order and second order reactions. And then you have plug flow reactors and then mixed reactors and the continuous mixed flow reactors and everything. So you have in the two tables, in the exam you want to pay attention that you're using the equation, right equation from the right table. So the first one is about the detention time or the hydraulic retention time. It's theta. Pay attention that is on the top, it says theta. The second one is for concentration. So we were going with concentration. Honestly, I didn't see the complete mixed reactor word over there, so I was confused why that solution came up that way. So you got to pay attention whether what it is asking, then look for the right equation in that in the tables. All right. So the right equation for the first order reaction would be theta, would be this, and then when you simplify this, this is what it will turn out to be, and then you get the answer. Now you should get 1.8, right? You can get it? Maybe my answer is wrong here, but it should be around there. How much you got? 1.8. Oh, he got 1.8. 1.8. Okay. Okay, let's look at two more new topics here at least before we move on. Go on to the page 3. Okay. So go on to page 3 and the top one. So a groundwater contains the following cations. Please read the problem, and I think I'll expect you to tell me the strategy to solve this problem. On page 2, that's about the hardness, right? That's hardness. A groundwater contains the following cations: sodium, calcium, and magnesium, and the concentrations are given. The total hardness is most nearly. So what do you think would be a solution for this problem? Yes, but what are the compounds of hardness?
The plus 2 ions.
That's right. So calcium and magnesium. So you can ignore sodium. Sodium is just given to you. Don't use sodium. So what do we need to do? So divide by, so the calcium and magnesium. And we need to get them in moles, right? Molecular weights, you're right. So now after that, what do we do? Multiply with the equivalent weight, right? Actually, you divide by equivalent weight, because once you get equivalents, you multiply with the multiply factor 50. That gives you as milligrams per liter as CaCO3. Milligrams per liter as CaCO3. Do you remember that? So the equivalent weight would be how much?
Just look at hardness, they still
That was really nice. Yeah,
Now, what does it give you?
working on it. Is that 12.13 or just 12.13?
12.13. Is that right, what I wrote on the board?
I hope so.
Where I got the 20 from?
It's probably 40.
That's 40 divided
Why
by
should it be 40?
40 divided by 2, number of electrons.
So that means 20, right? Is that right, what I wrote?
Yeah.
So calcium molecular weight is 40, but your equivalent weight is 40 over 2 because there is valence 2, so that will be 20. 20 milligrams per milliequivalent. So your answer actually would be in milliequivalents. Okay? So this would be milligrams per milliequivalent, so this and this will go for later actually. So then finally you multiply with 50. 50 again is another magic number, right? That's how you get milligrams per liter as CSU.
Guess what I got? Oh, that's right.
Okay, so much of fun. The FP. Oh. When I was taking this exam, I was like, you know, when I came out of the examination hall, I was like, I can't turn my neck. It was like 8 hours of just looking at the book and book. So tough. What's that? It was hard for me. I'm not intelligent. So, I mean, it's hard in the sense. I mean, if you're working on problems, you'll still be left with 10 problems at the end, and then you still have to do some guess, right? I've been working and working, then I was left with like 10% of those. For the last 10 minutes or so, then So what is the answer here?
300.
I have to see my answer. 300. Is that right? Brent, you got that? 300? You hope so? Okay, please look at the problem. Yeah, we're getting close to our time. The problem at the bottom, the activity of radionuclide, it's on the same page. The activity of a radionuclide was measured at 1200 BQ. What that is? BQ. Brian.
These guys.
You're actually looking at the wrong page.
Yeah, I'm looking at another problem.
Looking at, so you're all reading the problem? The activity of a radionuclide was measured at 1200. What's the BQ? Any idea? Everybody knows. That's the unit. But what is it? Yeah, I didn't hear that until I heard it for the first time. I never heard it before. Anyway, okay. Well, that's you got what I'm trying to say. All right. So you got to listen today. So BQ is I mean to you. I want you to laugh. Yes. So that's called a becquerel. A scientist's name. So you didn't hear it before, right?
No, did not hear it before. I've been educated. Thank you.
Is that how you measure radioactive material?
What's that?
Is that how you measure radioactive material?
That's the unit. So, if you read the problem, you know the problem, what the problem is about. Is that right, Scott? You did read the problem. So, how many of you know the solution for this problem?
We do that first sulfur.
See, this one.
We solve for our K's and solve for our T.
Exactly. I think it will require some T because the half-life equation would have a T in it. So this is asking you to calculate the half-life. So you're given information 1200 becquerels of initial value, and then you're given 150 Q BQ after a certain time. You're right. You get your T. So that's how you do that. You calculate the T, and then you will be using that information in your half-life equation. Let me find that equation. Actually, you're also given the time, right?
Yeah, good.
You're given the time, so you know what you're going to calculate then. You're looking for the K value. Actually, yeah. So let me write it. So N is equal to N naught e power 0.693 T times tau. I think I'll make it simple. Probably we should not use a problem. So T half-life is 0.693 over K. So you can straight away go and use the first order equation. I would say. Because no, tau is actually half-life. So you're fine. You're fine. So tau is actually half-life. You're given T. You're getting straight away your tau. How much is the time? 32 days. So that's the problem. Let me see what the answer is. Okay, you got the answer already?
11.
How many of you got 10.66?
That's what I got.
Something like that.
That's right. So these two actually look like the same thing, but they're same units actually. And they also have to have same units, right? Because it has to be unitless.
So, why do we just assume that this is first order reaction?
No, in this case, just look at this case, it's not a first, it represents like a first order reaction, but it is not first order reaction because you have, oh well, I see what your question is. This formula actually is also derived from that kind of relation, first order, it's assumed.
So, for all problems where we have something breaking down or degrading over time.
Okay. Now if you make some assumption like that, first order, you may be doing wrong. So you need to read the problem statement carefully. But in this case, what I want to say is the basis looks like the first order here, but it has a separate equation for it, like T over tau, right? So both of them are actual time functions there. So which is really, which is also interesting over there. So, did you follow what I'm trying to say? In this case, it happened to be the first order too. It's not necessary, but this formula is given to you in the formula over there in the book. But when you're reading the problem statement, you want to clearly see if it's saying second order, zero order, or first order.
In the problem statement, what lets us know that it's first order?
In this case, that's what I'm trying to clarify to you. We did not assume a first order. But when I saw the problem, you know that the problem is related to a radionuclide, some material, and then that is connected to half-life and those concepts. So what I did, I straight away went and looked for radiation equations, and then I grabbed the equation from there.
What page is that on?
Is that on page 178?
I think the first order is correct. I mean, I think half-life is derived from first order reaction.
So
That's
that,
what I was asking, yes.
yes, that's what I'm saying, but for in a real problem, you want to look for what it is.
You can say it's just decaying.
Yeah. So this one, yeah. That's the difference. Like if you're looking at the different problems. So. Okay, I think I covered some of the topics for you, because we could not cover everything. I think next time. Sure, you're welcome.